Tamam, tamam. Tamam.
Şu mu hocam?
O da görünüyor.
8 saniye geç geliyor.
Tamam.
Tamam.
Tamam hayatım.
O zaman başlatalım. Ladies and gentlemen, dear participants, welcome. İcmatse 12,000 conference. This session, fourth paper presented. Three papers. Hilal Kaplan. Sorry, Hilal Kurt. Please.
Okay, thank you. Thank you. I am Hilal Yücel Kurt, and I am professor at GAZİ University in Physics Department. I have three presentations today. First of all, I would like to thank the organizing committee for this valuable conference. And I want to start my first conversation about energy conversion via gallium arsenide electrode in a plasma system with microdischarge. İlerleyemiyorum hocam. Aha.
Geçeceğim bir saniye. Şunları da bir kabul edeyim önce hocam. Kusura bakmayın.
Okay.
Sizi bekliyorum. Şöyle. Hocam şuraya tıklayarak bir saniye öncelikle sizin sesinize bakabilir miyim?
İlerlerken nasıl güzel diye düşünüyorum ama sağdan soldan nereye giden şey yok. Basıyorum gitmiyor.
Gözüküyor mu? Şu şekilde hocam. Evet.
Hangisi? İleri
Bir saniye hocam. Aynen hocam. Şu. Şu ikisi.
Tamam.
Yukarı aşağıda.
Okay. Tamam. Okay. My first conversation presentation, which is entitled Energy Conversion via Gallium Arsenide Electrode in a Plasma System with Microdistance. There is a problem with my presentation because I don't, okay, I have no ability to progress. Gitmiyor. Sorun işte. Basıyorum gitmiyor.
Şimdi oluyor hocam. Şuraya hocam sıkıntı yaşadığınızda şöyle şu boş kenara tıkladığınızda devam ediyorsunuz.
Okay. The gallium arsenide electrode has been used as cathode, which is near infrared material that causes the conversion of the infrared energy to visible one. In the pressure range between 22 and 1 atmosphere pressure, it has a direct narrow band gap. Electron-based energy graphs and plasma formations were calculated with CAMSL simulation program. The energy exchange mechanism between cathode and plasma occurs when the appropriate plasma conditions are reached in the system. Elektron yok. Orada da görünmüyor, işte bir sorun var.
Bir daha hocam. Çok özür dilerim.
Tamam,
Pardon hocam.
Ben bekliyorum.
Kusura bakmayın
Yok,
hocam.
bence bir sorun yok.
Bir şey.
Bence sorun değil de.
Evet.
Biraz önce hocamı görüyordum ben ama. Nereden başlayalım? Tamam.
Hocam şuydu değil mi?
Aha.
GAZİ.
Kalbim Mersin Mert'e var. Hı hı.
Tamam, açalım bir daha. Niye böyle?
Yani sıkıntı yok.
Evet.
Sen görüyor musun ya da dursan mesela?
Hocam şöyle. Sıkın şey. Hı hı. Niye göstermiyorsun şu an? Whiteboard görünüyor.
İşte karşıdan.
Öyle bir sıkıntı yok şu an. Bunu
Kameradan
algılamıyor.
sonra.
PowerPoint şu an algılamıyor.
Algılamıyor
Hı
mu?
hı. PowerPoint ben screen sharing yapamıyorum.
Çözemedik mi?
Hocam
Başka bir-
PowerPoint'te screen sharing yapamıyorum şu an.
Başka bir şey var mı?
Kapatıyorum. Tamamdır hocam. İlerletebilirsiniz. Şu şekilde olması lazım. Şuradan hocam tıklayarak. Bakın hocam, evet. Aynen hocam, bu şekilde ilerleyebilirsiniz tıklayarak.
İşte o da olsaydı çok iyi olurdu. Okey. Tamam, okey. Siz başlatın hocam. Başlatın mı? Şu an canlı mıyız? Ha, okey, okey. Thank you. Tamam, okey. Okay, there's a technical problem, so we have lost time. So sorry for this inconvenience. Okay, my first presentation is about energy conversion via gallium arsenide electrode in a plasma system. The gallium arsenide electrode, as I said before, has been used as a cathode, which is a near-infrared material. Which converts the infrared light beams to visible one. Electron-based energy graphics and plasma formations were calculated with the CAMSL simulation program for the gallium arsenide electrode. The energy exchange mechanism between the material and the plasma occurs when the appropriate plasma conditions are reached. Electron-based energy graphs calculated with the CAMSL simulation program. Experimental plasma plots demonstrated the feasibility of semiconductor gallium arsenide wafer with an infrared detector structure. And our systems behaves like a microchannel plate and enhance the infrared light beams intensity. Due to the environmental problems, population and economic growth, present energy perspective skips to much clean, carbon-free, and renewable energy systems worldwide. While the traditional energy resources lose their popularity, solar, wind, and geothermal energy sources take interest for a much sustainable energy solution. The main objective of present innovations on the energy issues is to develop new sources with environment-friendly, easy applicable, cost, and constructively effective materials. As you know from the literature, gallium arsenide has been used for solar energy systems or energy conversion. The photovoltaic cells is one of the most preferred energy resources. For PV cells, the band gap of the semiconductor can be adjusted by alloying them with appropriate materials by using present laboratory conditions. The present band gap researches enable heterojunctions, which can be critical for the design of high performance efficiency optoelectronic devices, which can be used as PV materials. At present, PVs, which are widely used in many solid state applications, are usually made of semiconductor, such as silicon gallium arsenide. Development of thin film photovoltaic devices which can yield to sufficient efficiency are expected to reduce the cost of material productions. Because of the higher electron mobility of the gallium arsenide, low power consumption, and high breakdown field and the direct band gap, gallium arsenide is one of the most promising materials for PV industry. In addition, gallium arsenide has attractive feature with ideal direct band gap energy of 1.43 eV, and it is highly absorptive and relatively insensitive to heat. The last feature is vital since some caused overheat of PV materials can cause certain damage and fires on the PV panels. Gallium arsenide can be alloyed with many materials such as aluminum, phosphorus, indium, and has longer lifetime and high efficiency. The structure of gallium arsenide is zinc blend. Gallium arsenide is used especially for high frequency and high power semiconductors. And in this study, we use gallium arsenide with high resistivity because to avoid the damage comes from the plasma. Gallium arsenide has a wavelength of between 870 nanometer. It means it is affected from this wavelength, okay? Because we should choose the effective materials to detect infrared light beams and to convert them to the visible ones. Gallium arsenic containing devices are frequently used electronic circuits and transistor power amplifier circuits due to its wide energy band gap, as well as internet infrastructure, spacecraft, satellites, solar cells, GPS. So sorry. Circuits such as amplifier and RF switches, which require low voltage and can be used with energy sources such as batteries, replicate less in the large areas in our lives. Gallium arsenide is highly toxic material, and we should be careful for kidney damage and leukopenia, such as when we use the gallium arsenide toxic materials. Okay, we should choose some parameters to obtain optimal plasma conditions, and if we use the gallium arsenide as an infrared detectors, the detectors parameters such as first one is spectral response we should care, and the second is responsivity and quantum efficiency, very important to convert the infrared light beams to visible one. They are crucial parameters in our system. And if we think about the plasma, we have two important mechanisms. The first one is primary avalanche. The second one is secondary electron emissions. Those are generated by positive ions from the walls and cathode. Secondary electrons have enough energy to start the ionization in plasma, and discharge confinement occurs at only higher distance. This is the basic electron and positive charge transport mechanism. As you can from the table, a successive ionization process occurs when appropriate conditions are reached. And plasma is a good conductor of electricity and heat. Experiments clearly show that discharge in the air environment exhibit very different properties. In some circumstances, unstable simulation have also been identified. This is the microchannel plates, and we use such a structure in our systems. For example, this system is used for night vision devices, as we know, especially in military applications. And our systems, microplasma consists of gallium arsenide electrode. This is the cathode, and the second electrode is cyan dioxide film covered. And the system between this cathode and anode, the plasma occurs, but this microchannel plates intensify the intensity of the gas discharge. It is very important. So we use such a system between cathode and anode. And in this work, our aim is to find undefined plasma parameters experimentally, because we do not have ability and we need to another program like COMSOL multiphysics, because we can easily get undefined parameters by using simulation program. And COMSOL is very useful to define plasma parameters such as electron density and the temperature and space charge density next to the cathode, and mean electron energy and migrative electron flux. Those are very important parameters, and we never find these parameters experimentally. So we use the COMSOL multiphysics program in our study. This is mean electron energy graphs versus the pressure, and as we have seen these plots, mean electron energy decrease when the pressure increase. And for example, the A, elimle gösterebilmiyorum. Ha, okay. Çünkü şey olmadığı için tamam. The A plots belongs to mean electron energy graphs for 1000 volts, and the second one belongs to 1500 volts. And we easily see from the graphs that when we increase the voltage value between the cathode and anode, mean electron energy values are increasing. This graph, when we use our gallium arsenide meter as the cathode material, we observed electron distribution at different electrode distances and pressure and voltage. We show ideal formation operating in the glow discharge region under the favorable condition in the figures. At 300 microns, sorry, at 300 microns, electrons are in Aston dark space. This is a region with a strong electrical field. It has a negative space charge. The electron density is too small that it is not sufficient to excite the cathode. The cathode waits for electron excitation in an electrically conductive metal structure. We use, our studies are done in glow discharge region, and glow discharge region are separated to Aston dark space and glow discharge, and so our studies are included in Aston dark space in this part. And this is electron density for 2000 volt and 100 torr, and we can easily see that the plasma occurs between cathode and anode. The interaction between plasma and semiconductor influences system parameters. So it is easily seen from this graphs that we can obtain plasma under some conditions. This is again surface electron density graphs for 300 torr under 2000 volt. If the gap distance increases, the maximum current values will decrease. For fixed electrode spacing and fixed infrared illumination intensity, the variation of the maximum current with respect to the pressure is shown in figure. When the maximum current graphs are examined, it is seen that optimum diameter value is D22, since our system can work in wide range stability at this cathode diameter. This is electron density for we increase the pressure up to one atmospheric pressure, but in this condition our pressure is 500 torr, and when we increase the pressure, as you can see from the graphs, electron density are changing. Electron density values are very sensitive to pressure change. And mean electron energy, the first graph belongs to mean electron energy. The second graph belongs to space charge density, and the third one belongs to electron density. We have obtained those graphs by using COMSOL multiphysics programs, but at every conditions we do not reach to plasma, because if we want to get plasma, we should provide some conditions. Not every conditions we can get plasma. Those are very special pressure values, special voltage values, and special interelectrode distance. So not every conditions we can get the plasma between cathode and anode. These are migrative electron flux, electron current density under 100 torr. As we can see from the figure 2, if we look at the electron current density, electrons are separated in two groups between cathode and anode. The below ones belong to cathode. The higher one belongs to anode, and plasma occurs cathode and anode. But as we see from the second one, electrons have different energy values. For this reason, some groups are located next to the anode and next to the cathode. And again, migrative electron flux, electron current density for another pressure range, 220 torr. And as we see easily from the figures, the surface electron density, migrative electron flux are changing with respect to the pressure. And migrative electron flux have very different aspects as we compare to the other pressures when we reach the atmospheric pressure. 760 torr means 1 atmospheric pressure, so we can get our plasma results up to atmospheric pressures. And again, we can change the voltage value 150, and under the 100 torr, again we get different electron migrative flux, space charge density, and electron current density. Those are again mean electron energy, electron current density, migrative electron flux, but we changed the interelectrode distance. We fixed our interelectrode distance 50 micrometer. We can change the micro distance between 10 micron up to 1 millimeter. If we change the distance between cathode and anode, plasma have a very different aspect, very different appears, and we see this result from our graphs. Electron current density, electron density, and again are seen from the figures. And the voltage is 1000 volts, and the pressure is 22, and the diameter of the cathode 25 millimeter. Okay. These are the, again, towsend and glow discharge aspects which are get from our plasma. So those are 3D aspect of the plasma, 2D and 3D aspect of the plasma. When we look at this plasma appears, the second one shows very homogeneous, uniform structure. The first one has a bit roughly plasma. So we can get unstable or stable plasma according to the plasma parameters. In our experiments and our theoretical study, we use high resistivity semiconductor electrodes, and we studied gallium arsenide electrode, and we carry out our studies between 10 micron and 1 millimeter between cathode and anode, and our result shows that our experimental or console multiphysics results are very sensitive to pressure change, interelectrode distance, cathode diameter. So those are very important to understand energy exchange between cathode and plasma conditions. This is my first presentation, and you can, okay, second, okay. Which was the title? It is not important, I think. But I cannot manage to change my presentation. The second one is.
Sakin sakin. Geçeceğiz.
Okay, I can start with my second presentation. The second presentation is which is titled "The Micro Discharge Cell with Gallium Selenide Cathode Under Atmospheric Pressure Plasma." In this study, simulations were made with the help of CAMSL multiphysics program under atmospheric pressure in a plasma system using gallium selenide material. Space charge densities were found between different anode and cathode distance. And thus the optimal working condition which is required for plasma system for gallium selenide material were investigated. The boundary condition equations required for the formation of the plasma, gas, electron, ion, and particle equations in the plasma, gas discharge reactions such as elastic and inelastic collisions are calculated and integrated in the CAMSL multiphysics program. The ideal gas discharge reason for the plasma have been determined. We generated data using a DC voltage source for plasma that require power conditions such as AC. Because çünkü ben görüyorum da abstrakt görünmüyor orada.
Hocam şuradan.
Yok abstrakt hocam.
Hocam şöyle kullanabilirsiniz. Bir saniye geriye gitmek için burayı kullanın. Lakin şuradan giderken bu iki yana tıklayarak ilerleyebiliyorsunuz. Sıkıntı yok hocam dediğim gibi. Buradasınız değil mi? Evet. Tamam hocam şuraya tıklayarak şu tık yaptığınızda gider.
Tamam. Tekrar mı baştan anlatacağım? Okay. Tamam. Gallium selenide is narrow band gap 3-5 for semiconductor material direct absorption from the valence band conduction. It is tried for this material because of high of the resistance income radiation and the material is used as cathode in plasma. Gallium selenide is an important material, 0.67 EV due to its growing application in optic, electronic, and detector technology. Gallium selenide is a candidate for high-speed electronic and long wavelength photonic device. As we can see from the second page, gallium selenide is mostly used in optic, electronic detector technology, high-speed electronic and long wavelength photonic devices. Gallium selenide is an important material due to the increasing application in optic, electronic, and detector technology. Recent advances in fiber optic technology have supported materials suitable for device application beyond 1.55 micrometer. Gallium selenide is a candidate for high-speed electronic. It is very important and long wavelength photonic devices. Okay, the first chips and optic cable and laser application are seen from the figure or table, we can say. The feature of plasma is directly proportional of the quality of the cathode material and also optic properties of the material. On the other hand, secondary electron emissions mechanism have crucial role in the process. Secondary emitted electrons are related with the positive charge or space charges. We see from this graph Paschen curves. Paschen curves means that if we apply any power, any voltage to cathode and anode, while the pressure is changing, we can get this parabolic graph. It means that this parabolic graphs means that we can study in this region for plasma applications. Study of microgas discharge structures have important practical applications. Those plasma cells can be used as ultraviolet sources and also act important role in industrial applications such as purification and sterilization of material and also foods. As a result of many successive ionization in plasma interval, gas emits light in visible range depending on the gas type and external condition. In this study, we use conversion BEFA. We made our analysis with the help of CAMSL multiphysics simulation program, and 3.5 group gallium selenide vapor has a 1.678 EV band gap at room temperature. The optimal mesh structure, as can see, it's very, very high mesh structure we used for the resolution of our studies. And if we increase the amount of the mesh, we can get more clear, more true result. Mesh structure is very important for theoretical and simulation programs, especially for scientists. We used COMSOL multiphysics simulation program to get the electron density, space charge density for gallium selenide cathode. We noticed that both space charges are directly related to the plasma voltage and the pressure. Electron and ion particles in the applied electric field drift towards the electrodes in the system as a result of weak current. Space charge density are shown in this figure. Space charge are positive charge which are accumulated in front of the cathode. We have two mechanisms in plasma system. The first one is primary electron mechanism. The second one, secondary electron mechanism. But secondary electron mechanism is especially important to successive ionization process, because we can get electrons easily from cathode and anode system when we applied enough voltage to the system. This is a basic plasma result, but we can get secondary electrons from the cathode when the positive charge is hitting the cathode. That means when the positive charge next to the cathode, if they are hits the cathode, we can get voltage drop, and those positive charge also cause the secondary electrons which emitting from the cathode. So we have two important mechanisms. The first one, normal avalanche procedure to get electron mechanism between cathode and anode. The second is different from the first process, because second electrons are caused by positive charges. So positive charges result in secondary electrons, and those positive charges positive charges, as can see from, are accumulated from in two parts. So that space charge accumulated next to the cathode. Space charge density has been observed for this parameter for the interelectrode distance 100 and atmospheric pressure and 1000 volts, and we get space charge value around 3, as we can see from the computational result. And space charge density, again, we observed for different parameters. The interelectrode distance 50 micrometer, and P 1 atmospheric pressure, and the voltage 2000 volt. And if we change the parameters, as we can see from the graphs, space charge density are also changing. And we change the pressure and voltage between cathode and anode. And again, we can easily see that the parameters, when the parameters are changing, the value of space charge are also changing. For example, the first space charge density is about 3.49, and the second the space charge value is about 3.05. So when we get different space charge density between cathode and anode, if we change the plasma conditions. The formation and distribution of the plasma depends on time and plasma conditions. Space charge accumulation at the cathode is the main cause of the secondary electron emission from the cathode. This charge makes the electric field unstable and causes inhomogeneous electric field distribution throughout the plasma. We use the CAMSL simulation program to get space charge accumulation in front of the gallium selenide cathode. We notice that space charge are directly related to the plasma voltage. Gallium selenide is very good material for the plasma cell when they use as cathodes. Again, we see another electron density migrative electron flux for the interelectrode distance 300 micrometer and P 1 atmospheric pressure under 2000 volts. But we see from this graph those migrative electron flux and electron density have high energetic, because red one shows the high energetic plasma. The blue one shows the cold electrons. The red one shows the or belongs the hot electrons. So the temperature of the plasma is changing, but we are studying in the cold plasma under the cold plasma conditions. The temperature is changing little, not like fusion reactors, because it is a cold plasma between cathode and anode. Electron current density and space charge density, again, we see another under different plasma conditions. As we said before, plasma is changing according to the plasma conditions, electrons density and temperature, and pressure changing. Yeah, we have lots of parameters to change the plasma conditions. Space charge sensed electron and electron density have been observed for 1000 volt. We decrease the voltage. If we decrease the voltage, the color of the plasma is changing. It means the energy of the plasma changing and the transport mechanisms of the plasma are changing. The color shows what kind of plasma we have, what kind of energy electrons have. Again, I am saying that the blue ones shows lower electron energy and lower plasma conditions, and the red ones shows the high energetic plasma conditions. But we should put some limitations in our studies, because if we increase the energy, we can reach from the stable condition to unstable conditions. For example, we are studying at glow discharge region. We have three kinds of plasma. Those are Towson discharge, glow discharge, arc discharge. If we increase the energy of the electrons while the plasma parameters are changing, we can get the arc discharge. Arc discharge is unwanted discharge, because arc discharge is very high energy. It has very high energetic electrons and can damage to our system. And this is the last graph, belongs to this study electron current density and micronegative electron flux under 1000. The formation and distribution of plasma, as I said before, depends on time and plasma conditions. Space charge accumulation at the cathode is the main cause, secondary electron emission from the cathode. Those are very effective and crucial role in plasma studies. These charges make the electric field unstable. Secondary electrons and not secondary electrons, but space charge caused some instabilities and result in the inhomogeneous electrical field. We used CAMSL simulation program to get space charge accumulation in front of the gallium selenide cathode. We noticed that space charges are directly related with the plasma voltage. Gallium selenide is a very good material for plasma cells when they use as cathode. This is the second. Last one, but I need your help to change my presentation. I cannot manage and I cannot change the presentation. This last one.
Finish your or?
Okay, please.
Okay.
My presentation.
Okay. Which one is it? It's or? Okay. Okay.
This is the short one.
Okay. It's, yes, that's it.
Yes.
Oh.
No.
Which one is it?
This is this one.
Okay.
Third one. Okay.
Okay.
The third and the last one is about operation of lead selenide detector in the plasmic media. Lead selenide is very old material which are used in American Army in during the World War II, but they are very useful. They are very useful to get invisible image. So US Army used this material especially during the World War II. But we wanted to due to the aim of if we get optimal plasma conditions by using CAMSL multiphysics program for the first time, we use this material in this system for CAMSL multiphysics program. Infrared radiation sensitive devices development not only increases its popularity, but also hosts many different devices and applications. With the developing technology, the importance of semiconductor material in the market, industry, space research, fiber optic structure, defense, and weapons industry increasing. Especially this material is used for weapon industry. Semiconductor technology has come to an advantage position with the combination of DC, AC, and RF power supplies and group 6 elements from 2 and their usage in plasma. By using semiconductor in plasma, the infrastructure of tokamak, which is considered unlimited power source, and fusion energies, which are currently under construction, are also provided. In our study, the photomultiplier tube PMT structure, which is used in the military field and widely used in night vision systems. With the new technological developments and increase in semiconductor technology, plasmic formation, deficit semiconductors such as silicon and germanium can be operated with binary compact semiconductor and DC power and can operate with very little energy from the lithium formations. Partially excited gas, electrons, negative ions, and positive ions, and various excited atomic molecules. The infrastructure of tokamak, we know. We confined the energy in tokamak, and which is accepted as an unlimited power source, and fusion energies, which are still under construction, are also provided by using semiconductor in plasma. In our study, for the photomultiplier tube structure used in the military field and widely used in night vision system was reduced to minimum dimension, and a gas discharge system was created by considering gas discharge as a structure of the system. It is used in the manufacturing of interconnectors for thermal imaging. Especially used for thermal imaging. The mineral phosphor is a natural conductive selenite. It can be formed by reaction between lead and selenite. This selenite is one of the first minerals to be found to sense of infrared radiation used for military application, and is suitable for the use of structure from non-structured to high-tech structure with advanced technology. This selenite is a semiconductor material. They can operate at room temperature without need to cooling system. Cooling system, we use it at room temperature, and it is a direct band gap. 0.27 eV band gap. Nature, it also offers a very fast response, making this material an excellent candidate as detector of low-cost, high-speed infrared imagery. Lead selenite is a photoconductive material. The detection mechanism based on the change of conductivity of polycrystalline thin film of the active material when photons arrive. These photons are absorbed with the lead selenite microcrystal and then cause electrons to rise from balance at the conduction band. Lead selenite is thermoelectric material. Lead selenite nanocrystal embedded in various materials. Solar cells, because of its harmful effect on heat the environment, lead selenite should be used in laboratory environment by taking safety conditions. It is very dangerous material, causes damage to organs, suspected of causing cancer, and has a toxic effect. So we should care if we want to use this material as a detector material in our system. In our system, we use argon plasma. Why we use the argon plasma? Argon has a strong diffusion feature. Diffusion means discharge light emissions at different directions. So it has powerful, strong diffusion feature at the point of interest. The semiconductor materials which is used in this part, we use small in size, sensitive and expensive. In addition to life-threatening negatives such as material usage and sensitivity, high pressure and tension values have been eliminated. Before starting my presentation, I want to say that we did not get lots of graphs because it is very difficult to get plasma if we use this material. For example, when we use gallium arsenide and the other materials, we got lots of graphs, lots of plasma. But when we use, for some parameters, little plasma conditions are reached. It is because it is not a photonic device. It is used for the thermal imaging systems. Okay, we want to try this material as if it appropriate for our studies, not appropriate, but I think it should be used for thermal imaging systems because we use optic quantum detectors. So this is not very suitable for the plasma conditions under this circumstance because we have got little graphs, but I want to show these results briefly. Our plasma conditions, interelectrode distance D 3 micrometer, D is the cathode diameter, as you can see. For example, when we change the pressure from 22 to 300 torr, the value of the electron density is changing, but not a big ratio. Small changes we have observed. Their values are, I think, similar, not very big differences between these graphs. And migrative electron flux have been obtained, have been got for the same pressure values, and migrative electron flux, but very sensitive to pressure value as we compare to the first surface electron density values, because when the pressure is changing, migrative electron flux values are very sensitive, pressure changing. We can see this sensitive result from the graphs. For example, we got 1.26 10 to 25 value for 22 for migrative electron flux. And for example, when we increase the pressure 300, migrative electron flux value is about 2.73 10 to 24. So we can say that migrative electron flux values are more sensitive than the electron density when we changing the pressure values. Electron density, migrative electron flux, and mean electron energy graphs are obtained. P pressure value 800. We pass the atmospheric pressure. We increase the pressure and we got these graphs for 800 torr. Electron density for this value is very small. I don't know if you see this small plasma. Okay. I don't know. Very small. Very small. Because this material didn't give us very energetic, very brightness plasma, because this is very useful for thermal imaging system, not optic systems. So migrative electron flux is very little next to the cathode, as we see from the graph. And electron energy is along the cathode and anode is again not very high if we compare to the other materials. This material. And we change pressure as 160 torr, this material, electron density, and surface electron temperature, and surface migrative electron flux are also changing. But as I said before, these changes are not very important interval. So we can use this material if we do not have any alternative material, but the test or the another methods are more appropriate for the imaging system and plasma system than lead solenoid. Our ability, results, our ability to modify the microplasma system actually allow us to interfere with plasma as well. We can shape the plasma according to desired application area by using different distance between electrode, different gas usage, different voltage values, different semiconductor detectors. We can save voltage values, different semiconductor detector. We can save both time, money through the simulation program. We can see the consequences and negatives for plasma formation early, and we can process these aspects during the laboratory or application. Thank you for your attention. If you have any questions, please let me know. Okay, I can take your question. I can take your questions, dear. If they have any questions. No, I haven't seen any question. Okay. No, Okay. Question. Thank you for your attention. Thank you, organizing committee, for this valuable conference. Thank you again.
Okay. Thanks to Professor Kurt for all three presentations, nice presentations. We are ahead of program schedule. Anyway, we can go on. If Mr. Mansour is ready for presentation. Hello, Mr. Mansour.
Hi. I was really hoping to join you in Ankara today, but unfortunately, we'll be presenting online, if that is okay with you.
Okay, you can start with online connection.
Thank you. Thank you.
You can go on, please.
Perfect. Thank you so much. Oh, it says host has disabled participant sharing. Can you please allow me to share?
Can you share PDF değil, neydi? Your presentation?
It says that the host has disabled participant screen sharing. If you can just allow me from the security.
Ben bilmiyorum teknik şimdi o şey olmasın.
Okay, now it's okay.
Now it's red, I think.
Yes.
Okay.
Great. So you can see my screen.
Bunları kapatmıyorum. Okay. Okay, it's red.
Thank you very much. So without further ado, let's begin. Today, I'll be talking about high entropy diborides and how we are trying to make a difference using high entropy material through high throughput calculations and also the experimentations. This work has been a collaborative study between several groups across the globe. So we will begin without further ado. So ever since the beginning of human race, we have always been looking for super hard materials, materials that can cut through the steel, they can cut through the mountains, and they're everywhere. We use them as cutting tools, and they're just inevitable. We have to have super hard materials for the progress of humankind. Now, one of those materials is, of course, diamond, with an amazing, impressive hardness of 100 gigapascals. There is immense mining of it. There is immense lab-grown diamond material that we are using as abrasive powders. However, there are several problems with diamond as our go-to super hard material. Now, first of all, diamond is a high-pressure phase. We cannot produce diamond under low pressures using very simple methods. It requires extremely high pressures because when you look at the carbon unary phase diagram, of course, the stable phases for carbon to become diamond requires pressures in excess of 4 to 5 gigapascals, even at temperatures of over 2000 Kelvin. And if you just heat treat, or if you just try to produce diamond or expose it to pressures of about 1 gigapascal or lower at high temperatures, we would very simply see graphitization of this material. So for kinetic reasons, we have diamond, but for all practical purposes, from a thermodynamic standpoint, diamond is not a stable material, and it requires extremely impressive equipment to produce this kind of stuff, like these amazing presses that we see here that were developed in the General Electric in the 50s. So today, there are these immense factories where we see diamond production going on in China, in the US, elsewhere. But just to give you a glimpse of how difficult the process is, when we look at this diamond right here on the right side, this 20-gram piece of diamond, it took 14 days to produce. So this is not a very simple material to have. So the question is, what kind of material can replace diamond as the super hard material for our cutting tool purposes? Now, when we look at the material phase space in general, there are these amazing possibilities that we have yet to explore. So there is this beautiful question by Professor Brian Cantor that I'm just truly in awe of. So he says, if you take your periodic table and you just consider 60 of the elements that are abundant and easy to work with, and consider the combinations of these 60 elements, how many material are there and how many of those material have we explored? So the answer is, ever since the beginning of the humanity, we have only explored this tiny, tiny, tiny fraction of 1% in comparison to what is possible out there. So even if we look at it from a statistical perspective, the possibility that we will find the next super hard material amongst these high entropy materials is just inevitable. The next super hard material must be a high entropy material. Now, out of these high entropy material, there are a plethora of different possibilities. But just to consider why we have to explore the high entropy material, we can look at this graph right here on the left side. It seems that when we look at the average of the possible engineering properties of the precursor material in comparison to the high entropy, it is very clear that the high entropy materials can generally outperform the precursors. Very interesting. The high entropy material, when they come together, the elements as one by one on their own, can generally cause stresses in the material which do cause certain very specific properties of their own. Now, amongst those, for the high entropy borides, which were first discovered in 2016, we can see that these class of material can show extremely high hardnesses. They can show extremely low thermal conductivities, and they have generally sluggish diffusions. And they're also extremely cheap when we compare them to, for example, let's say diamond. Now, this first material was just discovered in 2016, but this first paper has already been cited 600 times. So this is a very active area of research. The way that this material actually operates is that we have these planes of randomly oriented cations of general transition metal. And then we have these two-dimensional boron planes in between these transition metal planes. Now, when we consider this kind of material, again, what we see in comparison to the rule of mixtures, some of these material can definitely outperform even in the hardness. So just look at these numbers here. They're about 25 gigapascals. Hardness for diamond, it was 100, still a big gap. But this gap could be potentially reduced if we do a very extensive search of the high entropy phase space, high entropy boride phase space. Another interesting observation that people have had with this material is that when we look at the oxidation curves, if you expose this material to oxygen, the high entropy borides generally show lower oxidation when compared to their precursor boride phases, for example, in comparison to titanium diboride or other ones. Something that is very important to note here is that this material does not require synthesis at high pressure. This is stable even at room pressures. So any kind of conventional sintering process can work, which makes this material very, very cheap. Now, a recent study from our group was actually something that I am quite fond of, by our friend Sina as the first author. We had actually looked into the hafnium, titanium, tungsten, zirconium diboride, and we calculated it from a density functional theory point of perspective, and it was also synthesized and sintered. Now, I would just like to point your attention to these two figures that have been highlighted in red. The calculated hardness of this material using density functional theory was 31 gigapascals, and the experimentally found was 32.8 plus minus 2 gigapascals. So you're generally in the range of what was found experimentally. And when we look at the Young's modulus, the calculated value was 490.11 gigapascals, while the experimental value was 490.5. So again, we were within that region of the experimentally found values. Now, we have to note that when we're considering these DFT calculations, there are no empirical inputs. So this is a fully ab initio result that we get from considering the atomic structure and the atomic Wyckoff coordinates of that particular crystal structure. This means that DFT can be actually quite trustworthy when we are considering mechanical properties of high entropy material. This actually poses a question, and that is, how many possibilities do we have? And what if, instead of first synthesizing and then characterizing our material, we do a extremely extensive search of the high entropy diboride phase space through DFT to find materials or compositions that can outperform in terms of their hardness, for example. So we considered the B group transition metals those are the titanium, vanadium, chromium, zirconium, niobium, molybdenum, hafnium, tantalum, and tungsten in their diboride phases. And if you just consider the possibilities, these are about 382 possibilities if you consider equimolar transition metals. And amongst these, when we do the DFT calculations, we do find several that are quite interesting. So the way that we do these calculations, again, we are using Vienna ab initio simulation package, and we're quite lucky here at ITU to have access to Turkey's largest supercomputer, the UHEM. And we, of course, that is not enough. So we have also developed a UHS system where we do extremely fast sintering of these material in a matter of minutes, and we densify them, and then we can actually experimentally verify those computational findings. And what we have found so far, amongst the calculations which have been done as of now, are several high entropy diborides with hardnesses in excess of 40 gigapascals. So that's good. That's really interesting, because the diamond's hardness was 100. Now we're getting a little bit closer. That's good. And amongst these, we have also sintered this particular phase, tantalum, zirconium, titanium, chromium diboride, in a single phase manner with an impressive hardness. So what we're looking at is that in a near future, it would become possible to actually plot the findings as new Ashby diagrams in order to demonstrate the high entropy diboride phase space in terms of their hardnesses, fracture toughnesses, and so on. But without, I wouldn't want to give a spoiler, so I would just say, please stay tuned for our upcoming paper, where we will actually present a lot of these details in great presentations of experimentations and computations at the same time. So I would like to end here and just appreciate the supervisors who have definitely helped immensely in building up of this work, especially Professor Zuhal Er, Professor Kamil Şele from Warsaw, Professor Mustafa Urgen, Professor Lütfi Oveçoğlu, and Professor Duygu Ağoğulları. And also, this work would not have been possible without the computational grant at UHEM, and also the powder synthesis part was through the Boren for which we are thankful. I'll be more than happy to take any questions you may have and proceed accordingly.
Okay, any questions from all or participants with online connected? If no question, we can complete the presentation. Okay, if any, please look. Soru var mı soru? Okay, no questions. Then thanks to Professor Mansur again for nice presentation. And we can go on with Mr. Hassan. Okay.
Thank you so much. Thank you.
We thanks. Kim hocam? Şunu okuyamıyorum gözümde. Kim diyor Hasan?
Hasan Elif Gezgin. Elif Gezgin.
Hasan Elif Gezgin. Ne?
Hasan Hoca bizim hoca Elif Gezgin.
Ha Elif Gezgin. Ha.
Ama gelmemiş. Yok.
Elif Gezgin is not here.
Var hocam.
Sinan Kavak. Ha, o musun hocam?
Burada yazmıyor hocam. Yok burada. Burada Elif Gezgin diyor ama az bekleyelim bakalım. Saatimiz var herhalde. Peki. Ilgın Hanım, sıradaki sunumu siz mi yapacaksınız?
Evet, ben yapacağım.
Tamam, o zaman biz hazırız. Siz şeyinizi başlatabilirsiniz.
Tamamdır. Okay, so everyone can hear me or the presentation is appeared, right? So I can stop or continue.
Hocam pardon bölüyorum, özür dilerim Ilgın hocam. Siz hangi salondasınız acaba?
Ben bir önceki salonda da olabilirim de benim physical participation'da hani online olarak katılacaktım. Linki kullanın dediler bana.
Anlıyorum. Sizi biraz bekleteceğim hocam. Hocam siz A'dasınız. A holündesiniz. Şu Ankara'dasınız yani. Bu şu an C salonu. Şu an kimlere geçebilirsiniz?
Vallahi bana linke direkt tıklayın dediler. Hani online yapacağımı söylediğim için.
Tamam hocam, sizi biraz bekleteceğim. Siz bana chatten, özelden numaranızı gönderebilirseniz sizin iletişim bilginizi alayım. Ona göre sizinle iletişime geçeyim. Olur mu?
Olur, yalnız sunumum başladı, tamam, ben şey yapacağım.
Aha, tamam hocam, çünkü yanlış holde olduğunuz için şu an bizim başka bir sunumumuz var.
Tamamdır. Ben o zaman direkt diğer linki şey yapayım. Olmadı iletişime
Tamam hocam,
geçerim
olur.
ben.
Olur
Tamamdır,
hocam.
teşekkürler.
Ben hatta hocam şöyle yapalım. Ben size atayım kendi numaramı. Eğer bir sıkıntı olursa
Tamamdır.
bana ulaşın. Tamamdır hocam.
Tamamdır. Olmuyor hocam. Şu an GAZİ olmuyor. Evet, şu an ben gördüm de. Sesim açık şu anda benim.
Özlem hocam merhaba.
Merhabalar, günaydın.
Hocam günaydın. Sizi bekliyoruz. Eğer müsaitseniz, uygunsanız başlayacağız ama kimin sunum yapacağını şu an bilemedim.
Mehdi yapacak ama biz Erol hocamla
Biz birlikte beraberiz.
Ha, Erol hocam merhabalar.
Merhaba.
Tamam. Merhaba. Hi, Mr. Hassan. Hazırsak başlayabiliriz. If you are ready, we can start.
Yes.
Okay, go on. Please.
First of all, share screen.
Ekran paylaşalım mı? İzin ver.
Bizim nereden? Özlem hocam.
Şu an
Şeyden izin vereceksin. Şu şehir etmesi için izin veriyorsunuz ya. Nereden veriyordunuz onu? Şu kızı bir tane.
benim ekranım geliyor sanırım.
Açabiliyor musunuz hocam?
Şu an benim ekran gözüküyor mu sizde?
Sunum formatına geçirirseniz.
Tabii. We can start now. Okay. Okay.
Hello, I'm Mehdi Hassan from Polytechnic University, Department of Material Science and Engineering. Here our today's presentation subject is highly efficient chrome 6 removal from aqueous solution by tin oxide loaded with palm kind of shell biochar composite. Today we are talking about these topics. In these topics, we made our presentation with our teacher, Sir Özlem Altintaş Yıldırım, and my teacher, Erol Pelivan. And in this paper, one of my master's student, he helped to read this paper, Elif GAZİ. Now we'll start our presentation. First of all, we introduce what we will talking today. We'll talk chrome 6 biochar, tin oxide nanoparticles, tin oxide biochar nanocomposite in our introduction section. Then we'll go to experimental method of tin oxide nanoparticles, tin oxide biochar nanocomposite, chrome 6 removal experiment. And finally, we are going to result and conclusion. In this slide, we are talking about what is hexavalent chromium. A hexavalent chromium metal used in many industrial applications, primarily for its anti-corrosive properties, may be generated during welding on stainless steel or metal coated with chromate paint used in electroplating jobs with potential chrome 6 exposure. Chrome plating or electroplating, welding or cutting on stainless steel, grinding on object with chromate paint, painting operation and paint removal, glass manufacturing. Then we're going to talk about major health effects of chrome 6. Chrome 6 are effect in our body, and now we will talk this what kinds of problem are facing in our body using chrome 6. The US Environment Protection Agency has the drinking water standard of 0.1 milligram per liter for total chromium. This includes all forms of chromium, including chrome 6. Chrome 6 also having bronchitis and asthma, skin effects, chrome hole. Strong exposure to chrome 6 causes cancer in the digestive tract and lungs and may cause epigastric pain, hemorrhoids, vomiting, nausea, and severe diarrhea also. And this slide we're talking about how to remove Chrome-6 from wastewater. We are using chemical, physical, and biological process can apply to remove Chrome-6 from wastewater. Among these physical and chemical treatment methods, the scientific community has been paying close consideration to the adsorption approach for environmental protection. Activated carbon is one of the most used adsorbent materials because of its excellent chemical stability, adsorption ability, tiny particle diameter, greatest inner surface area, and active free electron orbitals. But this carbon is not proper for large-scale water treatment due to high production cost and difficulty of regeneration. As a result, the use of conventional adsorbent materials, we are using modified white brine aluminum, zeolite silica gel, surface baggage, bauxite, etc. Non-conventional adsorbent materials, coir peat, cethin, cetosane, alginate cotton, washed hydrogels have been started to be used. Although the conventional adsorbents are economically favorable, they have usually low adsorption efficiency and require large amount of adsorbent. In this slide, we are talking how we collect biochar. We are collecting biochar from industries, agriculture, forests, plants, animal residues, sea cells also, where biochar is key converting forest of resources such as wood dust, wood logs, along with greenery, animal waste, sea cells, and industrial waste. In this slide, we are talking about production methods and why we applied our biochar. Production method, we are produced our biochar from hydrothermal carbonization, flash carbonization, show pyrolyze, fast pyrolyze, flash pyrolyze, vacuum pyrolyze, hydropyrolyze. We are using to collecting biochar, we are use hydropyrolyze method. And also intermediate pyrolysis, torrefaction, gasification pyrolysis. And where we applied our biochar, we are applying our biochar used to as adsorbent material for various synthetic dye molecules from wastewater. Metal oxide biochar composites have lately seen steadily increasing use within adsorption and photocatalytic technologies. We are applied our biochar to investigate Chrome-6 removal performance of metal oxide biochar-based composite from wastewater. As a metal oxide nanoparticles, tin oxide nanostructure were synthesized with hydrothermal method. Wheel form canal shells, we are collecting from biochar wheel form canal shells. The impact of major process variables such as contact time, catalyzed composition, and pH of the Chrome-6 containing water was investigated, and the degradation percent of Chrome-6 were evaluated. In our next slide, we are talking about synthesis of tin oxide nanoparticles using hydrothermal method. Hydrothermal synthesis was used to produce tin oxide nanoparticles. First, we are weighting our tin chloride pentahydrate. First, then we are going to mixing and dissolving process. In this process, we are using 10 milliliter of distilled water was combined with 2.14 gram of tin chloride pentahydrate and magnetically agitate for 1 hour to produce a tin salt solution. Then we put it into hydrothermal reaction. The hydrothermal reaction was heated to 2000 degrees Celsius, 118 degrees Celsius for 1 day. Then the white nanoparticles were separated and cleaned with 10% ethanol. And this is the process we are showing with you. Then we are going to synthesis of tin oxide biochar nanoparticles. In this in this slide, we are talking how we collect tin oxide biochar nanocomposite. We are using two routes. The first route is pre-treatment of biomass, and second one is post-treatment of biomass. The first route, we are using biomass metal oxide nanoparticles and put it into this tube furnace for heating purpose. After 400 degrees Celsius and 400 degrees Celsius, and we are collecting our biochar metal oxide hybrid. This is our first way. And second way, first of all, we adding our biomass to putting into this tube furnace 400 degrees Celsius. Then we are adding metal oxide nanoparticles. We have preferred the first route was applied for fabrication of tin oxide biochar nanocomposites. And here we are talking about the determination of the produced nanostructure was investigated using XRD studies. The XRD studies create this graph for us. This is our tin oxide nanoparticles graph. Here is the diffraction angles, and this is the intensity, concentration, intensity. The cluster structure and fast analysis of synthesis products are investigated by XRD. The average crystalline size of the produced tin oxide nanostructure was calculated using the Devessier equation. Here is our morphological analysis. This is created by chain of tin oxide nanoparticles. In this slide, we are talking about fast and crystal structure analysis of tin oxide biochar nanocomposites. This figure shows XRD fast diagram of tin oxide biochar nanocomposites. XRD pattern exhibits various additional peaks indicated the formation of mineral crystal and other inorganic materials. If you see this picture, you understand the characteristics of tin oxide peaks. And this is our morphological analysis of tin oxide biochar nanocomposites. Here is our low and high magnification SEM micrographs of tin oxide biochar nanocomposites. And now we are going through our next slide. These are in this slide we are talking about result and discussion of chrome 6 removal. Effect, this graph shows us effect of initial chrome 6 concentration on the removal activity of tin oxide biochar nanocomposites as a function of time, monitoring the degradation of chrome 6 under UV light irradiation and using 8-watt ASRAM UVC lamps as the UV light supply allowed to access the photocatalytic of tin oxide biochar composite. For each measurement, we are using 5, 10, and 25 ppm chrome 6. And finally, we are getting a good result from 10 ppm chrome 6. This will shows the degradation of 99.6. In this next slide, we are talking about here we are tested catalyzed concentration of tin oxide biochar. We are used 20, 40, and 30 milligram of the catalyzed concentration. Finally, we are getting a good result from 30 milligram of the catalyzed concentration. It will shows us the 99.6 degradation rate, and we decided to using this catalyzed concentration to remove chrome 6 from washed water. In our next slide, this will show us the excited electrons can convert chrome 6 space to chrome 3 waste, can subsequently be removed as the solid participate. And we are in our last slide, we are talking about conclusion. As a conclusion, It has been proposed to combine adsorption and photocatalytic system to get around the disadvantage of the existing technology and provide more effective and ecologically friendly chrome-6 removal. This study focuses on the remote photocatalytic achievement of tin oxide biochar composite that can be used in the treatment of chrome-6 from an aqueous solution. The biochar was obtained from wheel farm kernel shells. The tin oxide biochar composites were synthesized, and the impact of major process variables such as contact time and catalyzed composition was investigated, and the degradation percent of chrome-6 were evaluated. Chrome-6 removal efficiency is a vital consideration, particularly from human health. Thank you everyone for listening our presentation.
Okay, thanks, Mr. Hassan. We can take questions, if any,
Yeah, sure.
from online connection or from hall. No question.
Thank you very much for
Also, we thank you. We are now at the end of the program. We can finish the program. Okay.
Thank you.
Thanks to everybody. Goodbye.
Goodbye.
Welcome to the conference. Now we show the other speakers' speech. Now we start.
Hello, dear participants. I am Nizir, and I would like to present to you a part of Dr. Research and characterization of green technology based on fibers. So, let's start. First of all, our aim is creating a plant extract based on fiber structure by electrostatic level instead of the other conventional chemical methods. So first of all, we use green technology, and I would like to mention about green technology a bit. It can be summarized as non-technological efforts where green can be applied in both production and usage processes. And green technology and green chemistry include processes that are reliable because they prevent energy waste and avoid impact of waste. So green technology is also support this equation. Why do we choose fibers? Because we prefer them for many applications because they have high surface area and volume ratio, like the other size materials. They have high porosity, elasticity, and strength. And because of these advantages properties, they have many application areas, like non-basic in engineering. And filtration for metal removal and optical and electronical systems like wire protection, production, etc. We prefer electrostatic method to produce fibers because it's user-friendly and easier than the other methods which we use for producing fibers. We use molten polymer or polymer solutions by electrical process to obtain them. The system basically consists of three main components, like filling unit, where we use syringes to put the polymer in, high voltage unit for obtaining fibers, and metal collector for collecting fibers. I would like to mention its the method. Fiber formation is observed when we apply current exceeds surface tension of the liquid on the tip. By giving current to the middle tip and the collector, the fibers are collected on the metal target due to electrical voltage between them, and we can get easily the monocyte fibers. This is the electrostatic device which we use on that. You can see power supply, filling units, and the collector. Now I would like to speak of shortly fibers obtained from parts, the use of materials and their potentials for biological purposes has gained importance in the last decade. In literature, we can see many layers for making fibers such as henna, eucalyptus, lazy tea, aloe vera, etc. So you see we have pretty wide options to produce all fibers from plants. We use in the study onion, which is from onion family. Onion family is the oldest and is one of the oldest species. The most family members are onion and garlic. They are known. They are known in like because inflammatory and antioxidant not so much now. It still prevents they prevent blood aggregation and the blood, which is cause of the heart attacks and strokes, as you know. And we use propolis, also use propolis. Propolis has high flavonoid content, that's why it's effective against antibiotic resistance bacteria and has antimicrobial properties. And also, it has anti-inflammatory, antioxidant, microbial, and toxic properties also. I think maybe you have heard before, but it is a very important plant for medicine. Its usage is not come but gaining importance for the last 5 or 10 years. Because of that, they want to use it for our studies. It is a flavonoid species, largely from the roots of circulatory vitamins and the flora. It has anti-inflammatory, cancer, protective, and antimicrobial properties, and it has been tested for the treatment of many cancer types like liver cancer and leukemia. Also, it's found that its effects on Parkinson's and Alzheimer's diseases and ischemia. As I said before, we prepare onion propolis and white based on wax by electrostatic vessel, and we characterize them via infrared spectrum and scanning electron microscope. So let's start with fiber production. Since there is no previous study of onion-based fibers, we need to find an appropriate concentration and make a lot of experiments for that. We prepared 5 different solutions, which are include onion extract, and polyvinyl pyrrolidone, PYP. PYP is a non-toxic polymer, which has wide usage in herbal studies. So we want to choose them for our study. And we fed the solutions to the electrostatic device with these presented conditions. And gain these low fiber maps. As you can see, the great results of onion and PYP and our solvent and our solutions, we can see clearly onion, PYP, and solvent peaks on every spectrum, which are you can see, which are these and characteristic peaks. The spectrums are so similar as we designed. Okay, STM results are one of the most important studies for fiber studies. They're important for clearly determining fiber morphology. First 3 samples, we can see smooth and non-beady beadless structure, which are good for us. But as the onion extract concentration rise, fiber structure gets deteriorates and shapes like a jiggle form, which are undesirable for us. As we can see, the average diameters as the onion extract concentration rise, the fiber diameters decrease. So design diameter is changing. It depends on where you use it. Thick fibers are preferred in hard tissue applications, but thin fibers have more porosity, so they can be more suitable for cell studies. And so the diameters are not so much very important for us for the beginning, but we choose the first 3 samples for our experiments due to their smooth morphology. concentration. Our chosen amino extract solvents were combined with a fixed concentration of biplane and propolis, as you can see, 4% and 0.1%. These ratios have been determined after many trials, since there has never been any non-fiber before. They are hard methods also to speed. So we keep them the ratios fixed. So we use these ratios for biplane and propolis, and our chosen ratios for amino extract and PYP. So we prepared 3 mixed solutions from every plant and named them as you see. And now see the results again. First of all, we start by samples. In different spectrums, all these samples were shown same spectrums as we expected. We can clearly see sharp peaks of onion and characteristic peaks of biplane, as you can see in the control spectrum. As you can see in the control spectrum. And SCM results are quite successful. You can see the fibers clearly, beadless and smooth morphology. The average diameters were similar, but they haven't any significant difference. But we can say that as the onion concentration increases, diameter decreases. It depends on the viscosity decrease, I guess, which is sensible for us. And let's look at propose samples. In fact, results are similar like biplane. All the peaks, as we need to see, are clearly shown. You can see the propose peaks in other spectrums, which is important for us again. And SCM results. Propolis is the hard material to speak. Like I said before, so we need to use it for low concentrations. And you can see the smooth morphology, but nevertheless, we obtain thicker fibers. Like biplane fibers, when the amino extract concentration rise, we can see the diameter gets decrease a bit, but and because of the viscosity decreases, and the fibers can be suitable for tissue applications we get. So, conclusion. Onion examined mostly non-factors for as long as one cannot be found in so much. And also, there is no competition where onion structure what is done by are together. So we can see that GAZİ uses appropriate concentrations and not the rest of the effect of pharmacology. And we can say that onion samples are suitable to be used in tissue engineering applications in the form of fibers. And in order to support this study, we are also carrying on porosity and strength tests with antibacterial tests, of course. But for the beginning, these results are quite good for herbal non-fiber studies and contributes to the plant-mixture-based non-fiber studies. Yes. And my references to refer my presentation. Thank you to listening. Thank you.
Thank you for your contribution to our conference.
We thanks to this presentation for Ezgi Email, and we end of the this conference. We thanks for join this conference, and thank you for about. See you.